everyone. I'm Malaika. I'm going to talk to you today about colorism in high fashion, and more specifically how I was able to explore this issue using a bunch of different open source Python libraries that probably you guys have heard of before. So before I jump into the technical details, I do want to give you a little crash course in sort of racism in fashion, just so that we're all on the same page there. There's three things that I want to talk about. So the first is just the idea that fashion is super white, especially in America. And we can see a great example of that with Vogue magazine, a really iconic fashion magazine. Vogue literally means fashion in French. They've been around since 1892, and it wasn't until 1974, so 80 years later, that they put a black woman on the cover. They were making weekly issues at the beginning, and then they transitioned to monthly issues, and it still took over 80 years. So this is Beverly Johnson, and she was talking in an interview about what it meant for a model to appear on the cover of Vogue. And she says, this is our Oscar, this is our gold medal, this is everything in the industry. So you really can't overstate how important, how much of a milestone it is for a model to make it onto the cover of Vogue. And it took 80 years before that door was open to black women. So the next two things I want to talk about have to do with colorism. Colorism is this idea, so we have racism, which is prejudice against people of color, and then colorism takes that a step further, and it's the idea that there's further prejudice against people of color with dark skin when you compare to people of color with light skin. And you see this in a lot of different communities around the world. You see this in Southeast Asia and East Asia. You also see it in the Black and Latinx community, to the point where women will bleach their skin lighter to conform to that beauty standard. So if we look at Zendaya, this really popular actress and model, you might know her from Spider-Man or from 10 zillion other things. She has light skin, and she talks about how she thinks part of the reason she was able to become so successful was because she was sort of lucky enough to be born just conforming to this beauty standard. And she's very open about that. In an interview, she said, "I'm Hollywood's acceptable version of a black girl, and that has to change." So we can talk about colorism in one other way as well, post-processing. So this has two photos of this actress, Aishwarya Banchan, and you can see that on the magazine cover, she looks significantly lighter, right? Her skin has been adjusted so that she looks lighter. And when this magazine cover came out, I think it was in 2010, people were really surprised. They were sort of like, we know what you look like we've seen you before, and your skin isn't this color. And she was also surprised because this decision was made without her. The photographers and the editors at Elle decided that when she was on their cover, they wanted her to look a certain way. They wanted her to look very white, and they made that decision without her. And so that's something else that we see, is the use of Photoshop to lighten images. When I think about these issues of inequality and prejudice, I immediately look at them through the lens of data science, and I think a lot of you probably do as well. I sort of look for ways to talk about this that use statistics or visualizations, ways that will sum up this issue. And when we look at the first aspect, the idea that fashion is really white, it's pretty easy to get some stats from there. And it's been done before. So there's this piece called The Great Awakening. What they did is there's 6 magazines here, but they did this for actually, I think, 12 magazines. They counted the number of covers which had a non-white subject, and then they were able to graph this. So what they're showing is basically in the past few years, there's been a huge uptick in the number of non-white subjects on a magazine cover. And they gathered the data really well. I really encourage you to check out this piece. But they are missing some of the subtleties of colorism. This addresses racism, but it doesn't tell us about how those non-white subjects look. They could all just sort of be Hollywood's acceptable version of a non-white subject, and that's lost here. So I wanted to talk about colorism in a quantitative way. And to be clear, people talk about colorism a lot. Here's Alexandria Ocasio-Cortez. She's a congresswoman here in New York, and when she was photographed on the cover of Time magazine, she actually thanked the photographer for getting her skin tone right in the photo. She said, "It's the little things that make a big difference. A lot of people see and appreciate it." So this is an ongoing conversation that you see a lot, especially on social media, and there are a lot of pieces about this. But I felt that quantitative data was missing from this conversation, and that's something that I felt that I would be able to contribute that. And when you're looking for sort of a personal project or something you want to do when you don't feel like working on your homework in college, I would suggest that you look for an issue that matters to you, and maybe that issue is missing quantitative data, and maybe that's something that you can add to the conversation. Cool. So I worked on this with a publication called The Pudding. They do a lot of super great visuals and data journalism. I really encourage you to check them out. And for this project, we decided to look at just Vogue magazine. We felt it was super representative of fashion, and that sort of, we were able to look at how things change over time because they're issues. And so we came up with this research question, like, how do you turn a photograph of a woman's skin, in this case, the cover photo of Vogue, how do you turn that into a number? And this is a really hard question. Like, I sort of sat with this question for a while and didn't have an answer. So I decided to replace it with a question that I did know the answer to, so I could feel like I was making some progress there. And that question is, how do you turn a color into a number? And this is something we all are sort of familiar with. Like if you've used matplotlib or like updated the HTML on your Neopets page, you probably know RGB color representation. So you take a color and you're able to represent it with numbers. And RGB is probably the most common quantitative representation of color, but it's not the only one. One that I used was called HSL, so it stands for hue, saturation, lightness. And the lightness value will range from 0 to 100 or 0 to 1 depending on how you scale things. And a higher value indicates that the color is lighter, and a lower value indicates that the color is darker. So there's this question answered, like if we have a single color, how do we turn that into a number that represents how light a woman is? Well, we just convert it to HSL. We import some Python library that'll do that for us, and that's fixed. So now we can go back to this more complicated question. So we're working with a skin tone, right? Not a single color. And a skin tone has a lot of colors within it. Like if we look at this, this picture of Daisy Ridley, we can sort of zoom in on different parts of her skin and it'll return to us different colors. Like if we look at her forehead, then we get this sort of beige. If we look at maybe her cheek where there's more makeup, then we get this pink. Or we could look at the shadow of her chin and we'll get this dark brown. So her skin tone contains lots of different colors within it, and it's not obvious which one we're going to use when we're talking about converting this to HSL and taking the lightness value. What we want is sort of a way to summarize her entire skin tone. And that's, again, a tricky question, but what you can do is you can zoom in really far on this picture, you know, like you're in a cop show and you're like, enhance. And when you zoom in all the way, then you get something that looks like this. You reach sort of the building blocks of an image, the pixel representation. And each one of these cells, each one of these pixels, does have its own single distinct color value. And here they're represented in RGB. And when you're working with images, like all sorts of libraries, I used OpenCV, but pretty much any library that you're going to use is going to read an image in like this, a three-dimensional array. So 2 of the dimensions are to sort of capture that it's a rectangle. And then the third dimension is this inner list with 3 elements, the RGB color values. So before I was talking about summarizing the skin tone of a model, and that's a tricky question. But if I ask a room full of data scientists to summarize a list of numbers, you will all know the answer to that. So we can take the pixels that represent her skin, and this is just a list of numbers. And how do we sort of summarize that? We take the average. So we can take the average, and it'll give us back a 3-tuple, and that 3-tuple is itself a color. And so now we've been able to summarize her skin tone into a single color. And we have this workflow that's developed. So we start with we've got Rihanna here to demo the workflow for us. We start with an image of a woman. This comes from the cover of Vogue. And we grab all of the pixels that represent her skin. Then we average these to get a single summary skin tone. We can convert that to HSL. And then we sort of ignore the hue and the saturation components. Like those aren't really relevant to us. So we end up with this single number that represents how light Rihanna is in this image that was on the cover of Vogue. Cool. So I did sort of skip a pretty important step here. I don't know if you noticed, but when I was looking at this array, And I wanted to take all of the pixels or all of the cells that represented skin. I just sort of clicked and dragged them because there's only 20 data points here. And the images I was working with had a lot more than 20 pixels in them. They were generally 500 by 500, so about 250,000 pixels. And I didn't really want to be sort of sitting in my room all day tagging these pixels by hand. I had some more interesting things to do with my life. So what I want is something like this, right, where every pixel comes with a label. Some are labeled as skin and some are labeled as not skin. And then I can filter out the ones that are skin, and I'll use just those images, just those pixels when I'm calculating my summary skin tone. So this is sort of the dream. And what we've got here, if we squint a little bit and we look at this sideways, what we have is 20 data points, and each data point has some numerical features that are associated with it, and each data point has a label that's associated with it. And I want to use those features to predict the label. So you can see where I'm going with this. This is just a machine learning problem, and that's even more evident when I organize the data points into a table like this. We can see our 3 feature columns, and then we can see our label column. And the nice thing about having the data in this tabular form is that then we can do a little bit of exploratory data analysis, like we all know and love. Like I can plot these points in a 3-dimensional space because there are 3 features, and I've colored each one to sort of remind you of what these numbers represent here. And you can see that they split really easily into 2 clusters, and that bodes well. This is a great signal that I'm receiving, that this seems like a solvable problem. I'm going to be able to predict which things lie in which cluster, and that seems pretty doable. So one aspect of this data that's a little bit wrong in this representation is here I've got listed the label, and in reality I was dealing with totally unlabeled data. I didn't sort of go through and tag a few pictures to get training data. There were no labels at all, so it's a totally unsupervised problem. And what we've got here is a setup that matches k-means clustering really well. So raise your hand if you've heard of k-means clustering. Yes? Okay, cool. Raise your hand if you know the math behind k-means clustering. Okay, well, we'll fix that today. So the sort of ideal problem setup for k-means clustering is these bullet points. You have some data points. So here, one data point is 1 pixel in an image, and each image is going to be treated as its own individual data set. Then we have some categories. So here the categories that we care about are skin and not skin. And so those are the 2 labels that we're trying to end up with. Then each data point belongs in one of the categories. So this is really cut and dry. Like we want every pixel to end up totally sorted. We don't want any sort of maybe pixels here. And then the last thing is we have no access to tagged data, and that's what I mentioned earlier. So before I sort of dive into the math behind k-means, which I'm sure you're all super excited for, I do want to emphasize one thing. This is the data set that I started out with when I came up with this project, a data set of the models who have been on the cover of Vogue magazine. And I had this information about them, like their name, the date that they appeared on the cover, their race, a few other things. We tracked, I think, the photographer as well. And what my final goal was is to add a numerical column to this data set, which would be the lightness value. And that would be a single number ranging between 0 and 100, or 0 and 1, depending on how I scale things. So when I'm using k-means, I'm not using k-means on this data set. I'm using k-means on a different data set. So each row becomes its own data set. Like if we look at Renee Zellweger here, this photo of her is my new data set. And it is like a table with 3 features and a label that I'm going to predict. And I fit a k-means model to it. I record that information, and then I totally garbage collect that k-means model. I don't keep it around for anything. Then I move on to the next row, and this is Julianne Moore, and she gets her own k-means model as well. And so in the end, I ended up fitting about 250 different k-means models because every single cover girl got their own one. I really just want to be very clear about this because when we're talking about machine learning and image processing and people of different races, there's a lot of bias there, and we can talk about that all day. But something that crops up is you'll see people training models on images that look a certain way, like maybe only white people, and then they'll try and use those models to predict things about people who look a different way. And that's a very important issue, but it's not something that I was dealing with here because my model wasn't sort of remembering information from training data and trying to apply those patterns elsewhere. There was a new k-means model for every single image that I was dealing with. Cool. So let's go into k-means a little bit. And we're going to use Amal Clooney as an example here. So what I did here is I sampled about 1,000 pixels from this image randomly. And I plotted them in 2 dimensions. So here, red and blue. And that's just because 2 dimensions is a lot easier to look at on a screen than 3 dimensions. And so the way k-means works is you're going to start with 2 centers. So here they've been randomly initialized. Another way that k-means will do it is it'll select 2 data points from the data set, and it'll use those as starting centers. This works better for sort of this explanation. So then what happens is every single point calculates 2 distances, and 2 because there are 2 centers. So it calculates the distance to the red center and the distance to the blue center. And then whichever is closer, it gets assigned to that category. So if we do that for every point, then we end up with something like this. And now we reset. So we take all of the red points, and we average them together, and that's our new red center. And we do the same with the blue points. So that'll look something like this. And then we just iterate through this a lot. So we iterate and we reassign the centers and then we reassign the points, and we do this a few times. And there's usually some sort of stopping criteria, like maybe it'll be 1,000 iterations or something like that, to get you to converge to a point where every one of these data points, so in this case, every one of these pixels gets assigned to a category. And in this case, the categories are skin and not skin. So I fit my very first k-means model. And this is what it ended up looking like. So this is using red, green, and blue values as the features. And there were 2 clusters, skin and not skin. And what I did is I went through, and for every pixel in the image, if it was sort of tagged as not skin, then I painted it light blue. And if it was tagged as skin, then I kept it the same color. And so this was sort of my metric for measuring how well k-means was doing, is I would just look at this image and be like, yeah, it's pretty good. And so this was one of the first images I looked at when I had fit this first model, and I was super excited about it. And then I was like, look, I've done it. I've created the perfect skin detector. And then I started looking at some more images, and it doesn't always work that well. So this is, again, a new k-means model that was fit using red, green, and blue, and using 2 clusters. And then I looked at some more, and it was doing, here it's doing like a pretty bad job. It's missing a lot of her skin. It's including her teeth. And like the whiteness of her shirt, so not a great model here. And what I did is I sort of thought back to how to do the best ever machine learning. And the way you do the best ever machine learning is you start with an initial model, which I have, my RGB with 2 clusters, and you look at the metrics to see how it performed. So it was doing okay in some places and doing not so great in other places. And then you do a little bit of tuning. You adjust the features, you adjust the hyperparameters, and you sort of rinse and repeat. And if you do this enough times, then at the end you have the perfect model, right? And that's just how you do machine learning. So in this case, my features, I started with RGB, and I expanded them to also include HSL. I played around with using the distance a pixel was from the center of a photo. The idea was that skin is sort of concentrated in the center of a photo because faces are round and the image is square, but that didn't super work, so I ended up cutting that. Then for hyperparameters, k-means is really nice because there is exactly 1 hyperparameter, and it is the number of clusters. So my original idea was to use 2 clusters for skin and not skin, but what I found is in a lot of images there would be sort of 3 natural clusters. There would be the skin, the hair, and the makeup. You can see that with Amal Clooney's graph. Like there's the light brown, then there's the black, and then there's the red, which comes from her lipstick and her earrings. And if you imagine this in 3 dimensions, the 3 clusters are even more prominent. And so I sort of looked at these and I fit another model. And the next model that I tried was I used just red because humans have a lot of red in their skin tone, so I thought that would help. And I used 3 clusters to account for the makeup. And again, like it worked really well with Nicole Kidman. And then there were a few where it didn't do that great of a job. Like here, it's saying that the text in the background, that N that comes from the cover, it's saying that that's skin. And I didn't like that at all. And then there were some where it was just a mess. what have they done to Gwyneth Paltrow here? So I was like, okay, well, I'm stuck in this iterative loop, right? Okay, so I'm gonna like do some more feature engineering, change the features up, change the hyperparameters again, and I'm gonna do this again and again. And I've got this really nice function where if I just tell it what features to use, then it'll save all these images for me. And I got very stuck in that loop. And I ended up fitting 14 different combinations of these k-means models. So for a single image, I would have something like this. And one night, I was looking at all of these panels of images. So I ended up with about 250 of these panels, one for each cover girl. And I was like, I can look at this and I know which models are doing a bad job, right? Like these are performing really poorly, and it takes me 1 second to decide that. And I can also see which models are doing a good job, right? Like that's doing a really good job of getting her skin, and I know that. I can just look at it and I know that. And I was like, I wish there was some way where instead of automating all of this, like I am a human who knows things and I want to contribute that knowledge. And it turns out I'm totally allowed to do that. There's no one telling me that everything had to be perfectly automated. I just sort of got stuck in that because I think when we talk about machine learning a lot, there's this gold standard of like, we want to remove humans from the process. We want this perfectly automated pipeline. We just run it, we never check in at all, and things like work really, really great. And that had been so like burned into my brain that was what I was focused on. And my problem wasn't that I wanted to create the perfect skin detector. Remember, like that was never my research question at all. My problem was that I wanted to get 250 different lightness values for 250 different cover girls. And like, why not use a human to help do that? So this is something called human-in-the-loop machine learning. And you see it in a few different places. One place that it's really common is on forums where there's a lot of comments and maybe some of the comments aren't very nice. There'll be a machine learning algorithm that flags some comments for review, and it doesn't make a decision about whether to ban that user or to delete that comment, but it pushes those comments towards an admin, and then that human will look at it and make a decision. And so that's sort of what we ended up doing. So for this panel of images, me and an intern who worked at the publication, The Pudding, we looked at these panels, and then we decided, like, oh, hey, this one is good. Sometimes there'd be more than one. Sometimes there'd be like, this one is good as well. And we took these images, and that's what we used for the skin. And we averaged her and my results together so that things wouldn't be sort of skewed to my opinions. And so that was how we were able to turn a photograph of a woman's skin into a number. We used k-means to fit a ton of different models. Humans went through and sort of double-checked that the models were doing a good job. We extracted the skin as just a list of numbers and created a summary skin tone. We converted that to HSL and snagged the lightness value from that. And then we were able to make some plots. So here we've got a bee swarm plot. This was made by Jen and Amber at The Pudding. They're absolutely lovely to work with. A bee swarm plot is sort of like a more granular histogram. Like it's still one-dimensional, but in a histogram we summarize things into bars, and here we leave the individual data points. So we've got lightness on the x-axis, and then each point is sort of stacked so you can see where they tend to lie. And the colors are that summary skin tone that I talked about earlier. So when you look at this graph, it's pretty clear that Vogue does not put dark-skinned women on the cover of their magazine. This is 20 years, and I think anyone can look at this graph and say there were 2 or maybe there were 4 dark-skinned women on the cover of Vogue. And that's very clear and very obvious here. And I think that when you read a think piece or something like that about colorism, maybe you'll connect to it, and then it'll have this impact on you, and you'll realize what they're saying, but maybe it won't. And I think that you don't need to connect with this graph at all to know what it's saying. It's pretty clear what it's saying. And it's saying that like Vogue needs to do a better job. And with a lot of fashion magazines, it's the same way. So another thing that we looked at is this data over time. So here's a time series, and you can see this sort of fan shape as we get to closer years. We did this up to 2018. And so that sort of suggests that things are improving, like the range is widening. They've got some people with darker skin, they've got people with super light skin as well. And so maybe this is like a change. And we sort of dove into this very excitedly, and we found that what happened was they put Lupita Nyong'o on the cover 4 times. She was in 12 Years a Slave, and a lot of other things, us very recently. And so if we remove her from this graph, then there's no fan shape at all. So there's actually no change over time. This is something that's called tokenism, and if you check out the article that we ended up writing, we go a lot more into depth about that. But the idea is sort of, we thought that Vogue had started putting dark-skinned women on their cover, and actually what they did is they found one dark-skinned woman that they like, and they just sort of used her over and over again. And that's really not okay at all, and that's not a good solution to this problem. A solution would be to find a lot of dark-skinned women and put them on the cover. And so that's what I was able to show by sort of bringing quantitative data into this pretty qualitative topic. Thank you. Should I pass around the mic for questions? Yeah, then I will not have a mic. I don't know if that matters.
Hello, hi. As a sociologist working as a data scientist, I greatly appreciate your work.
Thank you.
We're relevant. And so looking at your work, so race is a very complicated thing, right? You know, it's skin tone in one sense, but it's also like culture, hair, et cetera, including assumptions about, you know, what certain groups can do, right? So this idea that, let's say, blacks are more athletic and whites are, let's say, more professional or whatever. With that in mind, I'm reminded of Ashley Mears' work. I don't know if you're familiar with her. She does sociology of fashion. Very, very smart. I think she's at NYU, but don't quote me on that. And she looks at sort of the high fashion, you know, where you make no money but have all the prestige, and sort of like being on the cover of like catalogs that has no prestige but actually pays bills.
Yeah.
And so I'm wondering if you extend this analysis to look beyond high fashion, if you see like a different pattern, right? The idea being, if you're selling athletic clothing, hey, you know, darker skinned people are more, you know, be very careful, worse athletic, let's put them on the cover to show like, hey, our clothes are, you know, for athletes or people with that sort of body.
Yeah. Cool. So there are two things that I think are relevant to that question. The first is the initial version of this analysis. It wasn't for Vogue covers. I used the models on the Gucci website and the models on the American Eagle website. So two very different clothing brands. One is very like fast casual and one is very high fashion. And I looked at the differences there, and what happened was basically Gucci had this very bimodal distribution where they would only have super light-skinned or super dark-skinned women to sort of get that like exaggerated effect that you see a lot in high fashion. And in American Eagle, it was a very smooth curve where they wanted to sort of get someone of every skin tone. Another thing is if we look at this, let's see, this plot. So these 4 points, 2 were Lupita and the other 2 were Serena Williams and Michelle Obama. And so we looked at sort of people who are on the cover who are models versus people who are on the cover because they're famous. And a lot of the black women who are on the cover were there because they were famous as opposed to because they were famous models. And so that was a distinction we noticed as well.
So are there any more questions?
Yeah.
I'm sorry if you already explained this, but how did you crop the faces so that they were standard size? Did you do that? Did you just have the intern do that manually, or?
No, I would never. Yeah, so I left out a few of the details about pre-processing because they were pretty boring. One thing I did was I removed the background of the images using this tool. It's called remove.bg or something, and it actually uses neural nets to identify humans, and then it wipes out the background. And then I also use just very standard, like out-of-the-box OpenCV to do facial recognition to crop those images down to size. And the facial recognition, that was more like human-in-the-loop machine learning. Like I checked, there were a ton of false positives that I had to like delete and get rid of. Those were the 2 types of pre-processing that I did. Cool.
Thanks. Lips. If natural, that is a skin color. If outlandish, then it's not. How do you handle that?
So that was something else that was more qualitative. Is when we were looking at like panels like this, when it was like very aggressive makeup and we felt that that k-means had even classified it as not skin, then that was a pretty good indicator. If it matched more their natural tone, then we were more likely to let it slide. Okay. Yeah.
I was curious in some cases if a cover girl happened to be in different covers across the years, if you checked if the same number was generated for the model or not.
Okay, cool. So I got a question about repeat models, so that's good. We unlock the bonus slides. So here's Rihanna. She was on the cover 5 times. A really cool thing about her is her lightness ranges from 0 to 1, and her lightness values spanned the range of 0.5. They varied that much across the covers. If you check out the article, which I will have a link to it here, or you can just Google colorism and high fashion. We have a tool where you can explore how different models are represented on the cover. I think Beyonce was on there a lot, and also Giselle was on there 7 times, and you can see that, generally women of color were photographed very differently, and white women were photographed pretty similarly.
Hi, have you thought about use CBCR instead of hue and lightness?
Say it again.
CBCR is like color blue, color green. It gives you the color and the luminosity, so you can exclude the luminosity and just keep the color.
So I looked at a few different ways to represent color. I didn't look into the one that you mentioned, but I did look into I think it's CMYK or something, and that wasn't really capturing what I wanted. I wanted the lightness value. Then also when fitting the k-means models, I tried fitting the model using just lightness or using just hue, which is sort of akin to the shade. And some of those performed well and some of those didn't. Okay. Also, if there's no other questions, this link contains a link to my GitHub, so you can see the code that was used to fit all of these models. Cool. Thank you so much for coming.